I guess I should introduce myself. I'm a cosmologist. Usually people don't do cosmology. Actually, someone just asked me what am I, and when I said I'm a cosmologist, then I said, "What? Not cosmetologist." It was a joke that kind of fell flat. I think we didn't know what cosmetology was. Anyway, people don't know what cosmetology is here either. Probably it's a good thing. It's something to change your face, in case you want a new nose, stuff like that. That's when I used to went to UCLA, the taxi driver assumed that I'm a cosmetologist when I say I'm a cosmologist. Ever since then, I just say I'm an astronomer, and then they said you're an astrologer, so my sign is so and so and so. So it got a lot better since. Maybe we should do a startup with astrology. That's what we were discussing earlier. Anyway, I'm trying to talk about learning the universe with machine learning. A bunch of you probably have heard some bits and pieces of this talk and how to open the Pandora box. And I was told that Pandora box is a bad thing to open recently. So maybe we don't want to understand machine learning at all. I don't know whether that's the case here. This work won't be possible without my students and postdocs. They're listed here. Siu He is sitting in the back here. Yingli is at Berkeley postdoc. Yufan is a Berkeley postdoc. Francisco's also sitting in the back right there. You can ask them questions later on. Wei Chan for Facebook. Simac is here, who's a machine learning faculty, and also sitting right there. Barnes Passos, right? He's giving a talk later on today, so you can definitely ask him more about what we've been doing. Eleanor Jill Summer is also sitting right there, so they were feeling frightened that I just called them out in the audience. Julian Oliver is now a faculty at Washington University, right? Did he move? Okay. North Chapel University. And Jeff Schneider at CMU is also faculty there. Lane Price, who was a postdoc, now is at Amazon. And Sebastian Fromentel, who's a postdoc with us, now is at faculty at UNAM also. So without them, it's not possible. As all the faculty knows, the faculties don't do that much work. We mostly just talk and tell them what to do. So these will actually do the real work. All right, so what do we know and why do we care about what we're doing here? As our universe as we know it, these are the fundamental questions that we actually recently found out. There are 27% something called dark matter. For people who have not seen the movie that you mentioned, Dark Matter, there's a bunch of movies. One involves Stanford grad students shooting all their visors. That's also a dark matter movie. And there's another dark matter movie that's actually referencing Avengers. This is like the cube that you have all the energy. They also call it dark matter inside. So different versions. That's not what we think dark matter is. Also not in the wine bottle here. But maybe it's weakly interacting massive particle. Large Hadron Collider is supposed to be built to look for this. But maybe the best bet is in cosmology because that's where we found it first, where we look at basically movement of stars around our galaxy and around the galaxy and realizing there's a lot more mass if Einstein's correct in the middle of it. That's how we found it. This is a strongly lensed galaxy image that is showing the Einstein ring. For those who likes keywords, these are really cool images of galaxies being, the light getting really distorted by a huge, massive amount of stuff in the middle that you cannot see. That's why it's dark. We have no idea what it is. And what is dark energy, which is 70% of the universe. And everything else we know is this 5%. This baryons, this covered us, anything that we can see and feel is this 5%. We've lost 95% universe to things we don't understand. And dark energy is something that's responsible for accelerating the expansion of the universe. Basically, the universe, as we expand the universe, if you don't know, the universe is expanding right now, and it's accelerating. There's more energy that actually is coming into that volume as we speak. And we have no idea how or why it works this way. Einstein has suggested something called cosmological constant, but he actually abandoned it back in the days, and people now resurrected it with this idea that maybe this is the clue to solve his equations without changing much of it. Somebody likes to modify Einstein's theory of gravity to also explain this away. We don't know what it is. It could also be very new physics, which we also don't understand. So I'll argue that the nature of dark matter and the nature of dark energy may be the two most interesting open questions in physics right now. That's a maybe, but arguably two of the most expensive ones. So Large Hadron Collider is looking for the dark matter. It's multi-billion-dollar experiments. I don't even know how many $billion it costs, but many, many. WFIRST telescope that we're about to build is like $4 billion. And there are many of these telescopes that's looking for simulations that you actually not simulation, these are real data that will look a lot better with WFIRST telescope, but these are looked at by the Sloan Digital Sky Survey telescope that Brice Menard just mentioned earlier. It observes all the galaxies. These are real data when you fly out from Earth. And you can see all these galaxies, they're real galaxies. That's why it's so fuzzy. It's not a simulation. And you can see this large structure. I want to point at this thing. These little cosmic web, these like spider web like, this cosmological structure of the universe. We want to use these as information to tell us what is the fundamental constants of the universe, such as how much dark matter there is and how much dark energy there is. Imagine if you change how fast the universe expands, you will change basically how big those big empty spaces and how fluffy those cosmic web will look like. So that's the idea, why this is so interesting. And we have no idea, there's no plausible theory that can explain everything right now that we have observed in the universe. So for the theorists here in the crowd, it's a challenge for any theorist to come up with a theory that explains even just the current observed quantities in the universe, coming from the high redshift, sort of baby universe picture called the cosmic microwave background, the middle pieces, which is like this, which is all structure of the galaxies that are formed, called the larger structure, and also the nearby stuff, which is exploding stars called supernova. All these three things basically tell you something slightly different, and no theories explain it. So I would argue that's one of the biggest questions in physics. So what do we usually do, given that we don't know what the theory should be? We take the distribution of these, cosmic web, at least from what I do. I study the middle part mostly, and not so much the earlier and the nearby parts. And then we combine it into some summary statistics on the upper right-hand side, which changes as some fundamental latent variables. So in this case, is how you will see, let me play this video again. Oops. This is changing as something called some parameter, basically a first order parameterization of this dark energy parameter. As you change it, you change the summary statistics of the universe. And this is basically the clustering statistics of this field. Okay, so this is called a multipole, and you have monopole, quadrupole, but it doesn't really matter. It's a summary statistics of about 20, 40 numbers. Okay, describe the whole universe. And then you can use that to what theory tells you and what the observable has told you, and combine to get constraints on dark energy. So that's the story. And you can also do that to understand what neutrino mass is. Neutrino mass are these ghost particles, that ridiculous number of them going through your fingers right now, and you have no feeling about it. Actually, I don't remember how many of them are going through right now. Do you remember? No. What's that? 65 million, according to Paco, going through your fingernails right now, and you don't feel anything. That's the neutrinos. And we can use the universe observations to describe how heavy these neutrinos are. So that's another interesting latent variables. So can we do better than what I just told you? Because this is what I usually do. This is my bread and butter work until I got tenure and I decided to be a little bit crazier. And because I met these machine learning people in Carnegie Mellon, it's all your fault. So I try to do something a little bit different. So can we use machine learning to help us understand the universe, to extract more information from the astronomical data set, right? We talked about taking this huge amount of data and compress it to about 20, 40 numbers. And this is a little bit of waste of information. Or maybe the universe is that simple, we don't know. So this is work with Simac, actually, Reifenbach, when he was at Carnegie Mellon. And we took a look at all these different simulations of different cosmological latent parameters of this cosmology universe. And we say, how about we take all these different simulations? They have different cosmological parameters. Can I go directly from this box to the latent parameters without going through the summary statistics that we were talking about before, which is what we were doing earlier. Okay? So no summary statistics, take that away completely. All right, we do that. And then we use convolution neural net. I think back in the days, it was a long time ago in machine learning, because it's 2016. 3 years is the eons in machine learning. This is very simple convolution neural net, but it was a 3D convolution neural net, and people weren't even doing 3D back then. I think that was one of the issues when we first started doing this. And we input little cubes of universes, and we go to the other side and say, tell me what the cosmological parameter or the latent variables are from these very complex maps. And we input n-body simulations, these interesting simulations of the universe with known cosmological parameters to train the convolution neural net first. And then we validate, and then we test. So here are the results. We have the ground truth versus the prediction. And just to draw your eyes the red dots is what I usually do, and that's what cosmology analysis is still using right now, because we summarize the statistics into certain formats and say here, and they do a maximum likelihood analysis. That's these billions of dollars experiments are doing, basically. And what convolutional neural net has done here is that it's actually shrunk the error quite a bit, and we actually ever since have even made the bias go away with a different training, I think better training. So then I asked myself, as scientists, I have many questions, right? So you see this, what I usually do is not doing very well, while convolutional neural net, who didn't know any physics, didn't have any training, did so much better. So I asked myself, can I get a correct estimate of the error, which is a paper that CEO and I and Simek wrote in iClear, I think 2017. We're not going to talk about it today, but then we're going to try to see if we can interpret the model learned in machine learning and just go directly to see whether machine learning can interpolate and generalize from the data just like human does, and be very provocative and say, can we find new physical laws? All right? Let's try to interpret the model learned in machine learning. So going back to this versus that, which is summary statistics versus just going full on neural net without really teaching any physics. We can design the following experiment, which I'll describe very soon, to learn the difference between the analytical modeling, which is my traditional method on the left, and the full information on the right, which is the machine learning model. And the difference between the analytical method and the full information is the fact that you need to simulate what gravity does to millions of particles over a huge amount of time. So that's what we actually need to do. In other words, can we understand what gravity does to millions of dark matter particles over many, many years without using a computer to simulate it at all? And can we use machine learning to skip, or maybe we can flip this around and say, can we use machine learning to approximate the whole complex simulation itself? So that's what we're trying to approximate with machine learning. Here's a simulation, a dark matter simulations. By the way, I use dark matter just as tracer of mass right now, just massive particles, because most of the universe are dark matter right now. And you can see that it's fairly complex dynamics. They're all gravity, but there are a lot of them and interacting over billions of years. So that's the goal. So the setup is on the left-hand side, we have inputs that are analytical approximation of the nonlinear universe. So we don't go directly to the beginning of the universe. We want the best thing the theorists can do. So best thing a physicist can tell you of the nonlinear universe, right? So start from there. And we want outputs, which are positions and velocities of all the particles evolved under gravity after X number of years. So in this case, 1 billion years. And we build a machine learning model in the middle. So instead of using numerical simulations of Newton's law for all the particles with smart algorithms to run really fast, which is what people usually do now, we will attempt to use machine learning to learn or interpolate from a large number of pre-run simulations. We call this the training data. So to give you a sense, one of these simulations that Paco run would take 500 CPU hours to run one of them. Okay, we'll attempt to reduce down significantly from there. So that's about 1.8 million CPU seconds. So we want to do this. On the left-hand side is analytical approximation. On the right-hand side, we want a prediction. In the middle is machine learning model that we use. It's a UNet. CEO can tell you way more about this than I can, and I'm sure there's a lot of experts in here. And in training, we use 8,000 pairs of this analytical approximation paired with numerical simulations. So the numerical simulations are the full nonlinear evolution of the universe, while the analytical one is the best the theorists can write down that takes basically no time to get. And fit into machine learning model, and we want to do this. So that's the final setup. How well do we do? We want to show the errors in something called the displacement field. For people who don't do physics at all, it's just the current position subtracted by the initial position. It's interesting to look at this because it's a combination of position and velocities. And we want to predict we'll look at two things. One is the benchmark model, which is what people usually do to make large simulations of the universe fast. That's what they do. That's what I do before I do this. And our machine learning model, the displacement field is what we're going to show. And the error bar here is from 0 to 5 megaparsec over h. 1 megaparsec is 3 times 10 to 6 million light years. 3 times 10 to 6 light years, sorry. All right, so here's the benchmark. You can see that that's the 2LPT, that's the benchmark predictions. And you can see that the maximum errors here actually are reached, and the maximum errors there are about 7 megaparsec overage. It's a pretty large number. And it actually correlates with the density of the universe. And here, which is our prediction here using UNet, is a lot bluer. So it's basically down here. The maximum error is 0.7. So it's about a factor of 10 better. And we want to check something more fundamentally interesting for the cosmologists here. We check the following, which is the average power spectrum of 1,000 simulations, just to mention to you that these 1,000 simulations took 30 seconds to run. Once you learn the model, it's 30 milliseconds each instead of 800 CPU hours each. So I don't know how many that's the conversion I have to do in my head. And then you can look at the average power spectrum of 1,000 of them. And power spectrum is basically just for a transform of the correlation function for those who don't do this cosmology. And you take the division between the prediction power spectrum divided by the truth in the middle. And something in the down there is basically the error power spectrum. So the lower, the better at the bottom line. It's about 60 million times faster. I did calculate it. And the power spectrum, as you can see, which I should jump over there, with our method. And 60 million times, well, faster than basically running the full simulation to the truth. So can we interpret the model learned in machine learning? So we can actually flip this question around and say, yes, we can approximate the complex 3D simulation a lot faster also, and it does really, really well compared to the current benchmark. And I want to move to the next part, which is more provocative, is can machine learning interpolate and generalize from data just like human does and find new physical laws? And if it does, then why? So what we did is that we actually did this for fun and didn't know that it will work. We started using analytical approximation map, not of the trained cosmology, but of a different cosmology. Dark matter density parameter, instead of 30% dark matter density, like what I told you earlier, the standard number, we use 10% and 50%. What does that really mean? If you look at the density and the displacement field plotted here, if you look at the two universes with 10% dark matter, which is here, and 50% dark matter, it's changing like from basically 10 to 80% differences. So it's huge change. We were talking about large change in the complexity of the simulation because you're talking about a lot less particles or a lot more particles, in terms of if you use the same universe. And let's see what happens. So we want to input this with a different analytical approximate maps, different inputs, but with the same neural net without retraining. No retraining at all. No meta learning, no transfer learning, none of that buzzwords that I don't completely understand. Can the learn model extrapolate and predict simulations that do not have the same cosmological parameters? By factors quite large, considering this universe have 30%. Now we went from 10 to 50%. So we checked the same thing that we looked at before, and here the maps are very similar. The plots are very similar. We looked at the average of the power spectrum, 1,000 simulation average, ratios to the true power spectrum, and the cross-correlation coefficients, but we're looking at the error power spectrum, which is 1 minus r squared. The solid line is the simulation truth. The long dashed line will be the predictions using the ML, and the short dashed line is the analytical approximation, which is the benchmark we're using. All right, so that's the answer that we have so far. Terms, but we don't have to go there right now. So I thought that was really interesting. We didn't overlap the training set with the test sets, which is very shocking for some people, at least for me, because that's not what I was taught. We did not explicitly use any transfer learning or meta learning. We did not, retrain or do anything like that. Maybe there's an overlap in information somewhere between these universes. Maybe the universe is fairly simple and there's a lot of symmetry so that it allows generalization and extrapolation by the network. It's easy, quote, quote. Maybe I'm finally gonna get famous. That's the afternoon talk. My possible climb to fame, for people who've seen this, you're probably not laughing anymore. There are two very important people here. The one on top is my husband, important to me, not to you, hopefully. The one below is Alex Honnold, who recently free climbed Yosemite and made a movie called Free Solo for those who watch any movies recently. And when I took this picture, it was like 5 years ago. I thought, this is how I'm gonna get famous if Pascal climbs really, really well. This is for those who climb, this is a 512, and it's not so trivial. But I think maybe now is to understand machine learning, or compressing the learned model into physical laws, or maybe discover new laws of nature. Or if I have to be super provocative, which are these interesting questions I'm asked to provide today, can we use machine learning as an approximate simulator? So what I demonstrated is that we can do it with a fairly complex system and approximate it and make it run 60 million times faster. That's a large number. I mean, I know we had discussion early on in the breakfast that says we shouldn't care about a factor of 10 if you can do million and billion times faster. Maybe, maybe not. How far can you push it? When does it fail for this approximator to work? Maybe it's just the symmetries and generalizations allowing us somehow. I don't know whether the symmetries is so important or is it so important in our particular approximation here. Maybe deep learning can learn the implicit physical model as we showed in the earlier section of the talk, where we can just learn the latent variables directly without going through any physics. It wasn't taught Einstein's equation. It doesn't know any theory. So why is that? Is it possible to understand machine learning or deep learning to be exact? Machine learning is much broader actually. So deep learning is so complex and it can do so many different things, and there's so many different types of stuff going on. Is it even possible to understand it? Is it something that's a pipe dream? Is physics, this is the provocative part for me, is physics necessary to understand deep learning? Like, is this something that we should look at physics because there are models for high dimensionality here, or is there something else we should use but not physics? Like, are we needed for this other thing that we do? Can we replace physicists with deep learning, right? So now we just talked about we don't need Einstein's equations anymore. We don't need gravity to simulate these simulations. It just learned from pre-run simulations. Am I out of a job in next, I don't know, couple years? Hopefully not so fast. Still need to raise 2 kids. And I'll end it with here, can we replace physicists with deep learning? Thank you. I would repeat the question. Lanka just said, is deep learning necessary to understand deep learning?
Physicists by deep learning, then in point 4 and replace physics by deep learning.
Oh yeah, you use it.
But there's no actually had an actual question.
Yes,
you have to.
I have an actual question. Sorry for. If I understood well in your second example, so you changed the cosmological constant, but you didn't change the training or the training set.
No, not training, because it's so expensive to run these simulations. We only have that many.
So it could fit. So the same network that you train,
exact same network.
And in the training set, did you have a range of these values of the cosmological constants?
One cosmological constant.
And it was able to recover the evolution with these new.
So there's some physics explanation I can go on about this, is that even for a universe with 30% dark matter, this is my theory, I haven't proven it. There are islands that are lower density and higher density. And then my training set for lower density universe and higher density universe, maybe. So that's one possibility, but we haven't proven that either. But there's no explicit overlapping of training set and test set. I'll let Stefan take over.
Okay, so in the order.
The simulations that you use, it's only dark matter, right?
This is only dark matter. I'm not touching anything else. We did use hydro for a different experiment that we actually just submitted the paper to arXiv today. But that's a separate paper. This is only dark matter and gravity only.
So you can you can learn uh, different values of the parameters that you're using, but you cannot learn new physics. I mean, this.
So that's a good question, right? Can we learn new physics when, if you don't put in the physics in a training set? That's a really good question. And I actually agree with, this was actually coming up from a conversation we had at DeepMind with your boss. I forgot his name. Schmidt. That's not your boss. Someone else. Anyway, Pushmi was suggesting that when I discussed this with him, he was asking whether knowledge discovery is possible here. Because whenever you have training set, you are assuming a physical model. And when can you discover new knowledge if you're always assuming something in your training set? And that's an interesting question. There's some ways to do it with GANs, I guess, to compare the data and the training. And if you see something different, that's a possibility, but that's going far beyond what I've done.
So if you take your simulation and initialize it from a particular state and then roll it out with two different cosmological constants, the one you trained on and the one that you tested on, what is the difference between those predictions? Do you see what I mean? So like, because if they make no difference, if at whatever the setting is, the cosmological constant doesn't have an impact on the outcome, but if it does, then like your unit error has to be greater than that error, right?
We did not retrain. So this is a very good question. So, but I want to show you the difference is here, right? So this is, you might have missed this slide. This is on the left-hand side, omega matter equals to 0.3, which is 30% dark matter. And the colored dots there represents the difference in relative error. So 0.8 is 80% difference in the density or the displacement in the bottom. And on top is when you have 10% dark matter, well, in the middle column, and the far right column is 50% dark matter. So those are quite different. We talk about 80% difference, or at least 10 to 15% when you look at the 50% dark matter universe. So they can predict really well to those outcomes. But one thing I want to point out to you that I think might have confused you is that we input analytical approximate maps of different cosmology, right? So we didn't change the training or the network, but we changed the input, which has information about the universe.
I see. Okay.
So the initiation is different.
I see. So then that carries
some information. Yeah. Exactly.
Yeah. No, I was just going to try to maybe clarify that it's the residuals, right? So if the residual is somehow universal, then it makes sense, right? And then the question is, it's a little harder to understand, but then your hypothesis is that the data has enough fluctuations in it that it gets to potentially learn some local rule, where in different cosmologies you're still probing those corners of like what the nonlinear effects are.
Yeah, so to clarify is that the analytical approximation is that, you kick the particles and they will go through each other usually. But if you use the full nonlinear, evolution of the universe, they will do this. The particles come in and they do that. And we're learning this, not the huge, trajectories that were kicked at the beginning and the initial condition.
So I wanted to ask a question. Is that so? In terms of like the 60 million, I mean, people do this also in particle physics, and you learn some simulator, and the simulators are expensive in a different way. And of course, a neural network, feed-forward neural network, is going to be arbitrarily faster than. But of course, you have to create the training data, right? So I think maybe the more honest metric is how many simulations do you need to run to train the thing, and then how many simulations are you wanting to do whatever your scientific goal is, right? And
That's excellent.
If it's like a factor of 2 or something, you gained a factor of 2, not a factor of 60 million, right? But if you want to do other cases, you might actually want to do this many times, and so then that offset is going to be amortized away, right?
So one thing, right? So this part of the talk, which is the test set and the training set are the same cosmology. Sure, it's 60 million times faster, but I wasn't that excited about it. It's fast, but as you said, I have to produce a training set. But if it does generalize and extrapolate, I don't have to produce a training set. I did not. So in this case, right, but that's a completely different cosmology.
Goal of however many simulations you're going to have to run with different numbers of cosmologies. Yeah.
So this is coming back to the question of, how many cosmological simulations do you need to run? In principle, you need to run a whole lot because you want to basically forward model the whole universe and compare with what we observed and hopefully find something different and see what the cosmological parameter is. So this is going back to the implicit model we were just discussing at lunch today. How do we find the correct model that are underlying in the universe? And there's a whole long discussion we should have in further days. This is David Bly.
Actually, the extrapolation, the error is a little worse than in the original training setting. Not worse
It's
at all.
more or less the same. I mean, that you can't see the difference between the long dash line, which is completely hidden. The short dash line here, the dotted line here, is the benchmark. It's not ours. You can barely see. Let me come point to you. That's the long dash line. I mean, they're just slightly off here, and you can barely see them.
So the blue is extrapolation and green is the first one we saw. I remember the first one was closer and the blue one was a little off.
So the blue one is a tiny bit worse than
Yeah.
the rest.
Yeah.
But the other two universes are all down here. So the point one is a bit worse in our prediction
I guess
than point five.
I'm just trying to say that what's the expectation, right? So you did get a little worse. Maybe not as we expected, but whether our expectation is reasonable, or this is still worse.
Yeah, yeah. We should definitely look into this. So we wanted to push it to fail. So that's what we're trying to do next, is to see how far we can push to this generalization and say, when does it actually fail and when does it not work? So that'll be the next set of work to do. There's a lot of work that I cannot show today, is how we interrogate the model to see what's happening.
Can you
That will
compare
be another half-hour talk, which I'm not going to go.
the training and extrapolating? Can you compare them? I guess it was kind of asked earlier.
Sorry, say that again.
The training set and extrapolation set. Can you compare some summary statistics or something to know?
They're very, very different. I mean, if you plot you can see it from the Powell spectrum. This is the Powell spectrum, right? So this is the power is off by multiple factors here. These are the three different universes. Correlation function, which talking about there's a lot less galaxies will be formed at this 10% universes. This is what we think is happening, which is in the orange, and the green is a lot more stuff and a lot more clusters. So the representation will be very different.
Yeah, but if your response is actually invariant in this direction where you see the difference, of course. I'm just saying that seeing a difference doesn't mean that it really explains the surprise.
That's a very good suggestion. So we should see, whether this local thing that, the stuff that it actually has learned is invariant to moving things up and down, basically in this map. We actually had somewhat related discussion.
You can have something being constant to this, and then of course nothing.
Right, it's the nonlinear evolution of the universe independent of the cosmological parameters. I don't think it's entirely independent, because otherwise we can't do a lot of cosmology. I know that in reverse. But yeah, this is really a good thing to try.
Remark to your provocative comment at the end.
Okay.
Actually, you need the law of physics because you need to prepare the training set. But whatever my comment, my question is, so here you modified omega matter. So did you try to modify other cosmological parameter, and did you try to consider modification of several of these parameter?
So we did try.
In this case.
So we did try. We don't only modify omega matter. We also modify AS, which is another parameter that for cosmologists you know what it is, and we also see similar behavior. But we did push it to somewhat failure mode as one test. I forgot which one it is in velocities, in one of the other cosmological parameters. So we're basically trying to push to see where it fails now, this generalization.
And did you modify more than one parameter?
At the same time?
Yes.
No.
I mean, you modified omega lambda probably with omega matter, but not. But you didn't try to modify several independent components. And do you think it will work? Okay.
This is for deep learning because we need labels, so don't worry about it.
So with Department of Training Data Generation, then that's not super cool title. I mean, it's worse than cosmetologist. so this one I know the answer to. The simulation is done for the last 20, 30 years, and they really well optimized. They're way, way, way better coder than I would ever be. And they've done it really well, and that's how fast it runs. And it's still 800 CPU hours. Francisco and Paco can comment on this. And I know CU worked really hard, and we worked hard, but I don't think we actually optimized the network at all. So, I mean, I think Thomas has done some work that can actually compress our unit to one layer and without losing too much accuracy. And we have 15 layers. So in some sense, we could have done it even faster.
About replacing physicists, I think you should be consoled by the fact that at the very least, physicists will make excellent conference organizers for the machine learning community.
I also have a backup job as a wedding organizer.
So I want to go on the replace physicist route. Have you thought, I mean, I understand you used a rather vanilla or generic neural net in some ways. Have you thought of putting some physics into the neural net to study this generalizability question?
Yeah, we actually thought about this, and we looked at Joan's paper actually not too long ago for this spherical CNN stuff. And there's multiple other, there's other things that we looked at. We tried a spherical CNN for a different problem, and it was not yours, but it's like a different implementation that was a bit slower than we expected. We haven't seen improvement dramatically from that, but I wonder if, so I haven't shown some of the work here. When we interrogate the model, it has learned spherical symmetry. So it's already learned rotational invariance by itself. So we didn't implement it, but it learned it by itself. So it learned the space and it learned the invariance.
Okay, the last question, because we are now.
You say anything about scales of the problem? So I know you have used these 1,000 by 1,000 cubes. And what about fast PM? Does that also use a discretization? And what is the scale of the two models and so on?
Yeah, so this is way beyond what I usually do because I don't actually run those simulations. Paco can probably comment on this in terms of simulations.
Like 1 gigaparsec box. And we can resolve unto 50 kiloparsec scale. These are the scales. I don't know if this was.
So 1 parsec is 3 light years, in case
Yes,
this makes some sense.
I understand, but I wonder if your ground truth model also has this scale that you artificially introduce by chopping up space.
Interesting. So you're
Yeah,
saying
so
that if there's some artifacts that we can introduce because we are not matching between the two, like the training sets resolution and our simulations resolution.
Yes, I wonder what it's probably true that fast PM also discretizes something.
They
right?
also discretizes.
Yeah,
Like they all started with a grid.
Yeah, and you probably use the same grid size roughly.
I don't remember actually.
Oh, you don't remember? Yeah, because it would be quite interesting to know what happens at a very small scale in fast PM and what can be preserved in your model.
So
and
we
so on.
retrained everything without fast PM now. So this is using the full embodied simulation. We retrained everything.
Oh, okay.
But everything's done with the best simulation we can get.
Even the full body is still discretized again, right?
Yes.
So at some scale, things will escape from any model at the moment.
Yeah. So the full embodied simulation, the best one we can run, are still discretized. Like it starts with a grid.